Through the millennia that human beings have existed, there has always been a fascination with the stars and the exploration of the unknown. Although we've been long able to predict the movement of the celestial bodies through careful observation and analysis, being able to physically explore space still is a theme of science fiction and futuristic utopias where humans are able to do whatever. Several discoveries of the past century brought us closer to a true understanding of the laws of physics and the fabric of the universe. One of the most controversial and often cited papers about deep space travel is Miguel Alcubierre's 1994 paper on warp drive, which heavily relies on the use of metrics and an understanding of general relativity. The challenge of faster-than-light space travel started in 1905 when Einstein published his theory of special relativity. In general, special relativity describes the relation between space-time dilation and contraction with the speed of the inertial frame of reference. We are therefore able to assume that space and time are relative to the observer, and this velocity is not absolute in all frames of reference, except for the speed of light. In his paper, Einstein established a universal speed limit, the speed of light. Nothing can travel faster than the speed of light, at least locally in inertial frames of reference. This can be better pictured by the equations, in which we can see that using a speed greater than the speed of light gives us inadequate answers.
Before, we observed that all particles in the universe under a certain gravitational field follow the same trajectory, with the same acceleration. We call this gravity. Yet, Einstein developed a theory in which the gravitation is explained as a general property of the universe. Curvature is produced in 4 dimensions due to the presence of high-density energy or mass, such that the behavior of a particle is based purely in the curvature present in the space. General relativity is a geometrical theory of gravitation. The relation between energy or momentum and the curvature generated is specified by the Einstein field equations, a system of partial differential equations. The geometrization of space-time explains why a free particle in flat space follows a straight path. However, when space is distorted, a particle follows a geodesic path between the space curvature. A fundamental aspect of general relativity is that it conserves the property in which all laws of nature are the same in all inertial frames, which means that the equations describing nature are invariant under transformations like Galileo and Poincaré transformations. Now, forces are unnecessary, so using field theories to explain interaction is a simpler and more beautiful way to explain nature.
The Einstein field equations are a set of 10 partial differential equations in his general theory of relativity. They describe the fundamental phenomenon of gravitation as a result of spacetime being curved by mass and energy. First published in 1915 as a single tensor equation, the Einstein field equations relate local spacetime curvature, expressed by the Einstein tensor G, and its corresponding metric with the local energy and momentum within that spacetime, expressed by the stress energy tensor T. The relationship between both allows tensor equations to be written as partial differential equations, whose solutions are the components of the metric tensor.
A metric is a mathematical function used to calculate the distance between 2 points in a physical space. In Euclidean spaces, we use a 2-dimensional metric to calculate an arc length. However, in special relativity, the metric changes due to the fact that at high speeds, relativistic effects change the way in which distance is perceived. Because of this, space and time need to be related inside the metric to make it function according to general relativity. The relation does not only depend on the speed of the object, but it's also affected by the distortion in spacetime caused by mass, momentum, and energy. As we mentioned before, this is described by Einstein field equations. Metrics in general relativity appear frequently as tensor. This is an elegant and easy way to represent a metric, as a matrix multiplied by its differential components. The metric we use in Euclidean space is this one. But in other types of coordinates, such as spherical coordinates, the metric we use is the following, in which we use the scale factors we have seen in other classes. This makes sense since they represent how the space coordinates are related and their curvature. And in the case of Alcubierre's warp drive, he proposed the use of a metric or space curvature, which gave the results he wanted. This is the one he used.
Alcubierre developed a mathematical model, specifically a metric, in which it is possible to travel at an average speed that seems higher than the speed of light according to non-local observers. Yet, it agrees with the main relativity postulates inside the proper frame of reference. The principle is simple. The spacetime is deformed because of high-density matter. This causes the metric to be altered. A bubble is generated between both perturbations of space. In front of the ship, spacetime gets contracted, and behind it, it gets dilated. This way, the ship could travel more distance in less time. However, for these spacetime alterations to be produced, according to Einstein field equations, exotic mass, as defined by Alcubierre, is required to produce that contraction. Proper matter, or matter as we know it, can only dilate spacetime. As strange as it sounds, the metric is based in Star Trek's warp drive. Alcubierre has commented that the idea popped up while he was watching the sci-fi series.
Miguel Alcubierre was inspired by the expansion of the universe to propose a distortion that would allow him to move through the universe at a speed apparently greater than the speed of light. The principle came from the observed fact that the length contraction and dilation can occur at speed greater than the speed of light. One example of this was measured by comparing the current size of the universe and the time since the Big Bang. According to what we know, the universe expanded at a greater rate than that of the speed of light. Miguel Alcubierre's distortion would cause a constant acceleration towards the desired direction during the first part of the travel, and a constant deacceleration of the same magnitude during the second half. This is all according to an observer outside of the spaceship, since inside there would be no acceleration or g-force. To create such curvature, he imagined a bubble with giant negative density mass in the back and positive density mass in the front. This would generate the effect he was looking for. The distortion is represented by the following metric. The bubble would figure a hat function, which can be represented by this graph. The hat moves through space as a function of the position of the spaceship, as we can see in the following formulas and graph function. As the spaceship moves forward, the top hat travels with it. And so, by altering the space behind it and shortening the space in front of it, the measured distance the spaceship traveled would be much smaller than what an outside observer would measure. Therefore, if the outside observer would shine a light on the desired location at the same time as the spaceship begins to travel, it would seem as if the spaceship was traveling faster than the speed of light. Yet, it wouldn't, at least in its inertial frame of reference.
Although the warp drive seems like a plausible idea at first glance, there are several and very important limitations for its implementation, such as the enormous quantities of exotic and regular mass in order to generate the desired compression and dilation of space. Even if we were able to obtain all that mass needed, there are still other objections, such as an incapability to communicate with anyone or anything outside of the bubble, and the danger of collision with hazardous objects in the path traveled.